Let's have a look at the first Geometry 2 theorem of the semester. Graph of a function is a chart theorem. It is a quaint little theorem, and which I like actually pretty much. There's a very nice geometric interpretation and corollaries. So, what is the claim? Well, let capital U be a subset of the k-dimensional real space, and let it be open. Moreover, let F be a map from U onto the onto the n plus k dimensional real space, and let it be smooth, or rather let it have m continuous partial derivatives, or rather m continuous differentiations, where m is greater or equal to 1. Then phi is a map then phi defined as follows. It maps an element u onto where u is from capital U, I'll write this in a second, maps it onto the ordered tuple of u, and f of u is a k-chart, and it holds that phi belongs into the set Cm. It has, again, m continuous differentiations. This m differentiable, m continuously differentiable. Now, we observe, actually, and I should write this, phi is a map, actually, from U as a subset of the k-dimensional real space. The dimensions will be important in the proof, so I want to point it out explicitly here. Phi is a map of U, which is a subset of the k-dimensional real space, into the real space of k plus n plus k dimensions, so the 2k plus n dimension. Well, proof now. It is easy. It's quite trivial. Now, clearly, phi is invertible. Why? Well, it can be quite easily explicitly written out. Basically, you can define simply the inverse of a tuple like this are the first k entries of the tuple. So quite clearly, phi is invertible. Moreover, phi is up to m times continuously differentiable, and I shall explain this in a bit. The rank of the vector derivative, Jacobian, of phi at some given u is equal to k. In other words, it is the greatest rank it could be, right? Why is this true? Well, again, let's make a little box here, because by definition, the Jacobian of f at u, or phi at u, is equal to the following matrix, where we have the gradient of phi at a, and oh no, not phi, well, phi 1 up to the gradient of phi of 2k plus n of a transposed. This is because we could define phi of u1, u2, dot 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 up to uk, and it's equal to the vector of phi 1 of u, phi 2 of u, dot dot dot, where phi 1 through phi 2k plus n are not vector functions. They are functions which have their image on the real number line. Okay, that image is one-dimensional. And my point is that this actually will look something like this. We will have a square I matrix, identity matrix, of dimension k, and here we'll have some rubble, here some garbage. It doesn't matter what's beneath it, because this ensures that I said before that phi is up to m times continuously differentiable. Actually, that was wrong language. It is at least m times continuously differentiable. And well, that's beside the point. Here, what is important is that we know that the rank of this matrix is precisely k, because we have simply k columns here. K columns. So it cannot be any greater, but at the same time it can't be any lower. So we can go on with the proof. The main question is, because we wish to prove that phi, as defined here, is a k-chart. Well, what do we need for it to be a k-chart? Well, if it were a k-chart, then it would have to be a homeomorphism. This means that it would have to have a continuous inverse map. So, yes, phi inverse continuous. Yes, it is. Why? Well, the reasoning for it is quite simple, quite straightforward. It is. Well, because, well, by definition, phi inverse maps u, f, u, which is some 2k plus n dimensional vector, onto u. Now, phi inverse is a vector function of at least dimension k. Well, a vector function is continuous if and only if every single entry is continuous. If because we have here we have explicitly written out phi using multivariable functions, but functions which are not vector functions, just regular functions, though multivariable. Phi is continuous if phi 1 is continuous, phi 2 is continuous, etc., all the way unto phi 2k plus n. Here it is the same thing. And we know for sure that every single one of well, maybe I should write it out explicitly. Phi 1 of u1, u2, u3, etc., until we arrive at uk of f1 of u, f2 of u, da da da, until we arrive at fn plus k of u is equal to u1, u2, da da da, until we arrive at uk. And here we are only dealing with constants, so phi inverse is a continuous function. As such, phi is a homeomorphism, and therefore phi is a k-chart. Hence, phi is a chart. And moreover, we also observe that every single one of the entries here is at least m continuously differentiable. It is continuously differentiable at least m times. These are constants, so they can be differentiated continuously as many times as one wants. And we know that from our assumptions, we know that f can be continuously differentiated at least m times. Hence, phi, well, both phi inverse and phi are at least m times continuously differentiable, which is wanted to prove here. Moreover, phi is, well, phi is m times continuously differentiable. And this concludes the claim. This is precisely what we wanted.